So we finish a consumer part from chapter 4, chapter 2 to 5, chapter 2, chapter 3, chapter 4. And chapter 5 we skipped. And we go today, forms theory. Forms theory is covered by 3 chapters, chapter 6, 7, 8. Okay? Today, chapter 6. Production. In this chapter, and the next, we discuss the theory of the firm, which describes how a firm makes cost minimizing production decisions and how the firm resulting cost varies with its output. There are 4 subsections. Subsection number 1, and firms and their production decision. Section 2, production with 1 variable input. Section 3, production with 2 variable input. And section 4, return to scale. Okay? Okay, the production decision of a firm. The production decisions of a firm can be understood in 3 steps. Number 1, production technology. How inputs, labor, capital, and raw materials can be transformed into outputs. This one mathematically formulated as production function, isn't it? Right? Like this. For example, Q1 is function of labor 1. That is one factor case, one factor model, right? And or 2 variable input is Q1 is function of labor and capital. That is describes production technology. Okay? And number 2, cost constraints. How inputs, labor, capital, and raw materials can be transformed into output. Right? Cost constraints. And input choices. Step 3, input choices. Just as a consumer is constrained by limited budget, the firm is concerned about the cost of production and price of labor, capital, and other inputs. Right? Cost. So think about cost curve in this 1 variable case. Total cost is equal to wage rate multiplied by employment of labor. That is total cost. Right? And in 2 good cases, cost is labor cost plus capital cost, isn't it? Right? That is cost function, cost constraint. Input choice is cost minimization problem. Now think about this kind of stuff. You want to minimize total cost. C1 is, now I would like to explain 2 good case. Then total minimizing cost, right, is WL1 plus RK1. Subject to, if you want to produce, Q1 is equal to Q1 L1 K1, right? This one is equal to, for example, 100 unit, right? You want to produce 100 pizza, right? With minimum cost. That's cost minimization solution. You can find L1 star and K1 star, right? To produce 100 pence of pizza with cheaper cost. That is input choices. Okay? Theory of the firm. Explanation of how a firm makes cost minimizing production decisions and how its cost varies with each output. Okay? Also, students already studied the profit maximization. We studied profit maximization in chapter 8, right? So, what is profit? Profit in sector 1 is total revenue. Total revenue when the market is perfectly competitive, P1 multiplied by Q1 minus cost, this cost, right? That is profit maximization. And you know, we already know that in introductory level, you find Q1 star, profit maximizing quantity of production, right? Maximizing firm's profit, Q1 star. Okay? In this profit function, total revenue and total cost. This total cost is actually minimize total cost in this process. All the cost is minimized cost. When Q1 is 1 unit, then you can calculate, you can find the minimized cost of 1 pence of pizza, 1 pen of pizza. And you solve Q equal 2, then you can find minimized cost when you produce 2 pence of pizza. This is 3, like this. We repeat this procedure, then we can find cost general or cost function, cost curve. Okay, so I'd like to explain how to connect cost minimization and profit maximization. Section 1, firms and their production decisions. Why do firms exist? Firms offer a means of coordination that is extremely important and would be solely missing if workers operated independently. Firms eliminate the need for every worker to negotiate every task that he or she will perform and bargain over the fees that will be paid for those tasks. Firm can avoid this kind of bargaining by having managers that direct the production of salaried workers. They tell workers what to do and when to do it, and the workers are simply paid a weekly or monthly salary. That happened because of existence of firms. The technology of production. Factors of production is inputs into production process. For example, labor, capital, and intermediate goods, intermediate materials. We can divide the input into the broader categories of labor, materials, capital, each of which might include more narrow subdivision. For example, labor can be subdivided, subclassified like this: skilled workers and unskilled workers. Skilled workers, carpenters, engineers, and unskilled workers. Also, skilled workers subcategorized by, for example, scientists and engineers, right? And just some experienced workers like this. Okay? So if we use some schooling years, right? So skilled, unskilled workers usually implies workers whose final degree is less than university. So simply talking high school graduate workers, right? And skilled workers basically implies university graduated workers. Schooling years is higher than 6 plus 6, primary 6 years, middle and high school 6 years, total 12 years. Schooling years less, equal or less than 12 years, unskilled workers. Higher than that, than skilled workers. Okay? Materials include steel, plastics, electricity, water, and any other goods that the firm purchase and transform into final products. Capital includes land, buildings, machinery, and other equipment, as well as inventories. For example, capital can be subcategorized into two basically: rent and capital, machine, right? That is machinery and other equipment. Production function, I already explained this, right? Think about this kind of thing. Our textbook use a small q. Firms production, small q, right? Industry production, usually large q. Q is equal to function of capital and labor. Production function showing the highest output a firm can produce for every specified combination of input. So this Q, output, means highest output that this firm can produce with this given capital and labor unit, right? So maximum production. Q means maximum production, right? Production function describes what is technically feasible when the firm operates efficiently, so maximum production. That is when the firm uses each combination of input as effectively as possible. Okay? The shown norm versus the wrong norm. Shown norm, period of time in which quantities of one or more production factors cannot be changed. That is shown norm. For example, usually capital stock is fixed factors, fixed variable, right? And labor is just variable. So labor cost is variable cost and capital cost is fixed cost in the short run. Okay? Fixed input, production factor that cannot be varied in the short run. Long run means amounts of time needed to make all production inputs are variable. Labor and capital is variable input rather than fixed input in the long run. Next slide, page 7. Average and marginal product, right? So I'd like to use a small q following our textbook. That is Q1, right? Or simply Q. So average product means Q over L. That is average product in one factor production function. Q over L, simply. That is average product. Average product of labor is like this, right? Q divided by L. Nothing new. And marginal product of labor is change in Q over change in L. That is definition. We already studied in Menkiv's Introduction to Economics book, right? And from here we know the table. This table shows amount of labor, right? Amount of capital. Capital is 10 every time, right? That means capital is fixed variable. Then total output is like this. So average product is total output divided by L. Then you can calculate the average product like this. And marginal product is changing when we moving here to here, 40 to 69. Change in Q is 69 minus 40, so 29, isn't it? And change in L is 4 minus 3, 3 to 4, so increase by 1 unit. So change in L is 1, so 29. Marginal product of labor is 29. Okay? The graphical illustration. Production with one variable input, one variable. There exists only one variable input, that is labor, right? Then production function is like this. From this production function, we can derive average product of labor and marginal product of labor. Okay? So that is marginal product of labor. That is average product of labor. The total output curve in A shows the output produced for different amounts of labor input. The average and marginal products in B can be obtained using the data in table 6 earlier table, right? At point A in A, you see blah, 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 blah. Okay? So I'd like to explain a little further for this, right? If production function x variable is L, y variable is Q, then usually shaped like this. That is production function. For example, like this, right? That is total product, production function. Then from here we can calculate average product and marginal product. How? First think about marginal product. X variable is same to L. Y variable is change in Q over change in L, right? That is changing rate of production function, isn't it? Slope of production function. So like this. What happened? Marginal products maximize at this point. From when we moving here to here, 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 like this, right? The gradient of this triangle should be marginal product of labor. Marginal product of labor is maximized at this point when L is, for example, L1, right? From here to here, what happened? Marginal product of labor increase and increase and increase with increasing rate, right? So like this. But after this, it becomes smoother and smoother and smoother. So marginal product of labor shaped like this, right? So how to derive average product, right? We studied that average, for example, at this point, average product at this point draw a straight line to the origin point. Then you can make this kind of triangle. Then the height of this triangle should be Q. Width of this triangle is L at this point, right? So tangent of this triangle is average product of labor, right? So, and from here, you can find the point of production, total product, where average product maximized. That is, for example, at this point is me, right? Average product maximized at L2. Okay? For this point, smoother than before. At this point, smoother than before. Right? So average product maximized at L2. And average product shaped like this. That is average product of labor. At this maximum point, this point, for example, average product of labor is equal to marginal product. Right? So average product of maximum average product of labor calculated using this triangle, right? How to calculate marginal product at that point? You draw straight line tangent at this point, then, right? This kind of straight line and make triangle and calculate gradient. That is marginal product of labor, isn't it? And you realize that this red line coincides with black line when we calculating average product of labor, coincide with each other, right? So same, at this point, L is L2, average product of labor is equal to marginal product of labor. Okay? Production with one variable input, blah, 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 blah. Anyway, we know that at this point, marginal product is equal to 0, isn't it? Marginal product is equal to 0, so shaped like this, right? So now sometimes I'll ask you, so what happened in point A, at point B, at point C? At point B, average product of labor maximized. Point A, marginal product of labor, highest numbers. Point C, total product maximized. So marginal product of labor is equal to 0. Okay? Average product of labor curve. In general, the average product of labor is given by the slope of the line drawn from the origin to the corresponding point on the total product curve. I explained this, right? And the marginal product of labor curve. In general, the marginal product of labor at one point is given by the slope of total product at that point. You draw straight line tangent at that point and make any triangle and calculate gradient. That is marginal product of labor, right? The relationship between the average and marginal products. In figure 6.1, the average product is the slope of the line from the origin, OB, and the marginal product is the tangent to the total product curve at point B, blah, blah, blah. I already explained, right? Law of diminishing marginal returns. Principle that as the use of an input increases with other input fixed, the resulting additions to output will eventually decrease. That is law of diminishing marginal product of labor, right? Marginal product of labor anyway decrease and decrease as labor input increase, right? That is law of diminishing marginal product of labor. You already studied this in chapter 18 of Menkes Introduction to Economics. Now, the effect of technological improvement, simply talking productivity growth or technological change in figure 6.2. Then what happened? Labor productivity, original product, total product curve is like this. So in production function, I said Q is function of labor, right? But there are some shifting factors. For example, technology level, right? When technology level, original technology level is T0, then production function or total product is like this. But technology level increase, this one increase, then production function shift upward like this. That happened because technological change, right? Technological change improved again, then write this. Okay, that is the effect of technological improvement. And 13. The example 6.1, the author debate a production function for healthcare. So the US case actually, right? Expenditures on healthcare have increased rapidly. Y variable is increased life expectancy. So you expand more, then expectancy increase, right? So that is output variable. X variable is input expenditure, healthcare expenditure. Then do this increase in expenditure reflect increase in output, or do they reflect inefficiency in the production process? Some authors argue, US economists discuss about this. Bob argues that the primary explanation is the fact that the production function for healthcare exhibit diminishing return. So shaped like this. In other words, marginal product of labor decrease, right? Because of this, marginal NPL decrease. So life expectancy doesn't increase, anyway increase when your healthcare expenditure increase, right? As healthcare expenditure increase, then life expectancy increase, but with decreasing rate, okay? In other words, decreasing rate, marginal product of labor decrease. Because of this, that is one argument. The other argument is that now, this one, for example, right? Some technical inefficiency happen, right? Production function means input, then output, right? So this output is maximum output when using this labor input. But in the United States, for example, there are some also said expenditure happen input here, but total production should be point E, but point D. Then inefficiency of input matter, okay? So there are two ways to look at the debate in the United States, okay? Now we go, next slide. Malthus and the food crisis. The law of diminishing marginal returns was central to the thinking of a political economist, Thomas Malthus. Everybody knows that Thomas Malthus, right? He is very insightful as a classical economist in the sense that he knows diminishing marginal returns. Okay? So Malthus predicted that as both the marginal and average productive labor fell, and there were more mouths to feed, mass hunger and starvation of the result. So really gloomy projection of capitalist development. What is his idea? You hire more labor, then you can produce more food. But production function is shaped like this, right? So we can find the marginal product of labor decrease and decrease. As you hire more labor, right? Then food production increase. As labor input increases, food production increase with decreasing rate. Simply talking, marginal product of labor decrease. But mouths, right? The households increase and increase. Okay? Demand increase and increase. But output increase with decreasing rate. So mass hunger and starvation is the result. This is Malthus' basic idea. But, however, over the past century, the technological improvements have dramatically altered food production in most countries, including developing countries such as India. As a result, the average product of labor and total food output have increased. Okay? So, the main point of this phrase is that is true, marginal product of labor decrease. But the other thing happened. If we look at past centuries data, technological change happened, right? In food production function. If Malthus ignored increasing technological improvement, so labor increase, Q increase with decreasing rate, but demand for food increase more rapidly than food production, so starvation happened. But that doesn't happen because of technological improvement. Technology increase and increase. Okay? So in this graph, marginal product of labor is like this, right? Marginal product of labor is like this. Total production function is like this. When technological level is T0, technology improves, then production function shaped like this, right? Technology increase again, production function increases like this. Then what happens? Marginal product of labor originally like this, but like this and like this, right? So production increase. Production of food is not bottleneck. Bottleneck of some fully satisfy some demand for food, right? So look at this. So cereal yields, so food production index is like this. Food production increase like this, and price index is like this. Price of food decrease instead of increase in this state, in this period. In the long run, food price doesn't increase, simply talking. If production is smaller than demand, as Malthus predicts, price of food should increase, but that doesn't happen. Okay? And food increase greatly because of technological change. If we look at long-term insights, right? So long-term study of economics, technological change or productivity growth is really, really important one. But most of people ignore technological change and productivity growth, and always talking about some result, right? But if we look at in the long term, productivity growth increase almost 1.8% per annum every year. Labor productivity increase 1.8% per annum. Because of that, we can produce more, so we can consume more. Okay? Now we go next section. Production with one variable input, labor productivity. Average product of labor. Labor productivity is average product of labor for entire industry or the economy as a whole. Productivity and the standard of living. Consumers in the aggregate can increase their rate of consumption in the long run only by increasing the total amount they produce. I already emphasized. You can consume more because production increase. But lots of people think of only think increasing consumption, more consumption. But that should be accompanied by increasing production. Understanding the causes of productivity growth is an important area of research in economics. We do know that one of the most important sources of growth in labor productivity is stock of capital, right? Okay, I'd like to explain these things a little later. Okay, so labor productivity is this one, Q over L. That is labor productivity, isn't it? There are two sources of growth in labor productivity. Number one is capital stock, increasing capital stock. Number two is technological change, right? Technological change, right? So what's the meaning of this? Labor productivity increase, then you can receive higher wages. That happens because increasing capital stock. Now think about a pizza restaurant, right? So you cook pizza, two labor cook pizza with one oven, right? Now also the other is two labor cook pizza with 10 oven, right? Latter case is more productive than first case. So in other words, capital stock increase, then labor productivity increase. That is stock of capital. Okay. So now think about early stage of capitalist development. Lots of entrepreneurs want accumulation of capital to survive at the competitive market structure. They want to accumulate more capital to increase productivity, actually, right? And number two is technological change. Development of new technologies, allowing factors of production to be used more effectively. Everybody knows this, right? Labor productivity and standard of living. Will the standard of living in the United States, Europe, and Japan, simply talking rich world, continue to improve? Or will these economies barely keep future generations from being worse off than they are today? Because the real income of consumers in these countries increase only as fast as productivity does, the answer depends on the labor productivity of workers. Okay, now think about labor productivity in a different period. Anyway, positive, right? In the long term, about 1.8%, right? Japan, France, Germany, UK, like this. And now we move next section. Production function with two variables. Right? Production function with two variables, labor and capital. So first introduce isoquants. Isoquants curve showing all combinations of inputs that yield the same amount of food. The production function is shaped like this. Q equal function of labor and capital, isn't it? Right? So now think about, you can cook 100 pans of pizza. The production function is L1 and K1, right? That is, using this, you cook 100 pans of pizza, for example. Right? That is one isoquant. When X variable is labor, Y variable is capital. Then you can draw some isoquant, one isoquant. The shape of isoquant is perfectly same to indifference curve, isn't it, in consumer theory. Right? That is isoquant. Also, you can draw labor and capital combination to produce 101 pans of pizza, or 110 pans of pizza, 200 pans of pizza, like this. Then we can graph isoquant map, right? Isoquant map is shaped like this. Labor, capital, that is Q equal 100, labor and capital input mix to produce 100 pans of pizza, 150 pans of pizza, like this. Lots of some isoquant curve, right? When produce 1 pan of pizza like this. All of this one, isoquant map is graphical illustration of production function, isn't it? Okay? That is explained here. Anyway, if we focus on one isoquant, there are lots of ways to cook 100 pans of pizza, right? In combining 1 capital, 1 labor, and 5 capital oven, or 2 capital and 3 capital oven, or 3 labor and 2 capital oven, like this. There are lots of ways. Labor and capital combination, that is isoquant. And the isoquant map graphs combining a number of isoquants used to describe a production function. So isoquant map is a graphical illustration of production function, okay? Like this. Figure 6.2, a set of isoquants or isoquant map describes the firm's production function. Output increase as we move from isoquant Q1 to Q2, Q2 to Q3. So pizza production increases 55, 75, 90 pans of pizza. Okay? Output increases as we move from Q1 to Q2 to Q3. By drawing a horizontal line at a particular level of capital star, for example, 3, like this, we can observe diminishing marginal returns, right? In the shown labor production function is like this, isn't it? Production is function of labor and capital. In the shown capital stock is constant number, fixed at 3 oven, right? 3 oven. Then we can move A to B to C in the shown to produce more pizza, right? Only increasing labor, holding capital oven employment constant at 3. Okay? We can observe diminishing marginal returns. So we can find diminishing marginal returns. Reading the levels of output from each isoquant as labor is increased, we note that each individual unit of labor generates less and less additional input. We moving A to B, labor increased by 1 unit, but production increased by 75 minus 55, so 20. When we moving B to C, 90 minus 75, so 15, decrease. Marginal product decrease, 20 to 15, okay? Improve flexibility. Isoquants show the flexibility that firms have when making product decisions. They can usually obtain a particular output by substituting one input for another. it is important for managers to understand the nature of this flexibility. Even though both labor and capital are variable in the long run, it is useful for a firm that is choosing the optimal mix of inputs to ask what happens to the output as each input increases, with the other input held fixed. Because adding one factor, for example, one labor, while holding capital input constant, eventually leads to lower and lower incremental production of pizza. The isoquant must become steeper as more capital is added in place of labor and flatter when labor is added in place of capital. There are also diminishing marginal returns to capital. Okay? So what's the meaning of this? I'd like to explain using this one graph. So the idea is perfectly same, right? So now, for example, you hire 3 labor and 3 capital oven and produce 100 pans of pizza, right? Now you, for example, that is 5, that is, for example, 2, right? Anyway, at point A and point B, production function means 3 labor input, 3 capital input, right? Leading to 100 pans of pizza, okay? At point B, 5 labor and 2 capital input also produce same 100 pans of pizza a day, for example. Same, isn't it? Right? So then we can make this kind of triangle. Right? Now we say this is a point C. What is point C? Point C means you hire 5 labor, 3 labor, and 2 more labor. So 3 plus change in L. Labor increased by 2 units, 5 labor, right? And held capital input constant at 3. Then you can cook more pizza than before. That is 100, but for example, that is 150, right? Then you produce 150, isn't it? Right? Now think about movement A to C. Only labor input increase, held capital input constant. Then you can cook. Change in Q is 50, 150 minus 100. Change in Q is 50, isn't it? Right? You can cook 70 pans of pizza more when labor input increase. Simply talking, change in L multiplied by marginal product of labor is equal to plus 50. Okay? Now, move on to C to B. Move on to C to B means 5 is 3 plus change in L, isn't it? When we moving here, labor employment same, but labor employment decreases 3 to 2. So we can say this is a 3 plus change in K. Right? Change in K is minus 1, isn't it? Right? Then, what happened? We moving here to here, change in Q is minus 50. Right? Why that happened? Because you hire less capital open than before compared to point C. So movement to C to B is change in K over marginal product of capital is minus 50. Right? That is A to B, B to C. So A to C means change in L, MPL, plus change in K, MPK is equal to 0. Mathematically, this one. Right? From here, we can calculate change in K over change in L is equal to minus what happened? MPL over MPK, isn't it? Right? What is this? That is changing rate when we're moving A to B. When we're moving A to B, we can make this kind of triangle. The width of this triangle is change in L. Height of this triangle C to B is change in K. Right? The changing rate. So gradient of this triangle is changing rate when we're moving A to B. That is mathematically this one, isn't it? Right? So this one explained here. We said that is changing rate. Graphically, that is original function, and now L, same horizon x variable is same to L, y variable is changing k over changing L. Right? When moving A to B, that is equal to this one, minus, for example, something. Right? And slope means absolute value of changing rate. Right? Slope means absolute value of changing rate. That is MPL over MPK, isn't it? Right? That is simply talking MRTS, marginal rate of technical substitution. Okay? So changing rate is, how can I say? Changing rate is like this. And slope is changing like this, right? That is MRTS. If original function isoquant shaped like this. That is explained here. MRTS is absolute value of changing rate. So minus changing K over changing L. Diminishing MRTS. So from here we know that the value of marginal rate of technical substitution or absolute value of this one is decrease and decrease and decrease. Right? So that is diminishing marginal rate of technical substitution. Additional output from increased use of labor, MPL, change in L. Right? I already explained. And reduction in output, decrease use of capital. That is movement from C to B. That is MPK, change in K, that is equal to minus 50. So reduction in output from decreased use of capital is this one. So total change is this one, A to C plus C to B should be equal to plus 50 minus 50 is equal to 0, right? From here, rearranging this, we can calculate changing rate is minus MPL over MPK, and MRTS is like this. Okay? Next slide. Marginal rate of technical substitution, like the indifference curve, isoquants are downward sloping and convex. So downward sloping and convex, right? So that is negative. Labor increase, right? Then shaped like this. Original function shaped negative relations. In other words, changing rate is negative. Okay? And convex. Convex means decreasing MRTS. Then, or original function shaped like this. Okay? Isoquants are downward sloping and convex. The slope of the isoquant at any point measures the marginal rate of technical substitution, the ability of the firm to replace capital with labor while maintaining the same level of output. On isoquant Q2, what is Q2? This one. The MRTS falls to 1, 2 thirds, to a third. When you're moving here to your triangle, is very steep. That is 1, that is a third like this. Right? Decrease. The shape of triangle becomes smoother and smoother and smoother. Right? So MRTS decrease. Two special case of production function. The extreme case of production function shows a possible range of input substitution in production process. The case of perfect substitutes. Production function is perfect substitutes. Then perfect substitutes. Production function perfect substitutes. For example, labor, capital, right? Perfect substitutes. Then straight line. Right? Production function isoquant is just straight line. Then MRTS, right? MRTS or absolute value of change in K over change in L is just constant numbers compared to usual function. Quite different, isn't it? Right? And fixed proportions production function is like this. Fixed proportion function, for example, like this. think about Leontief production function shaped like this, right? Then MRTS is 0 or infinite numbers, okay? The L-shaped isoquant, that is fixed proportion production function, so that only one combination of labor and capital can be used to produce each level of output. Actually, we already studied this kind of form of function in consumer theory, right? Same to that. Next page. That is a perfect substitute case. When the isoquants are straight line, the MRTS is constant. Thus, the rate at which capital and labor can be substituted for each other is the same no matter what the level of labor input. Okay? That is fixed proportion production function. I already explained this. Example, production function for wheat. Food grown on large farms in the US is usually produced with a capital-intensive technology. Why? United States is a land-abundant country. Right? However, food can, and labor-scarce country. However, food can also be produced using very little capital and a lot of labor. Right? Most farms in the US and Canada, where labor is relatively expensive, so they want to produce same good with using more land and less labor. Okay, but developing countries is just the opposite. Right? Developing countries is labor abundant country usually, right? So they want to produce same unit of agricultural good combining more labor and less capital, less land than United States case. Isoquant describe the production of wheat. A wheat output of 13,800 bushels per year can be produced with different combination of labor and capital. For example, at point A, 500 labors and 100 some acres of land, capital like this. Right? That happened in the US, but developing countries produce same amount of food using more labor and less capital, like this. Okay? So at point A and point B, we know that so MRTS have a different value. Right? At point A, MRTS at point A higher than MRTS at point B. Okay? Now finally we study return to scale. Rate at which output increase as inputs are increased proportionately. Increasing return to scale. What is the situation where output more than doubles when all input doubled in this production function? Right? For example, input doubled, then total production is equal to 2L1, 2K1, isn't it? Input doubled. Right? Then output more than doubled. For example, 3Q, like this. That is increasing return to scale. Okay? Decreasing return to scale means situation in which output less than doubles when all inputs are doubled. Input doubled, but total production is, for example, like this. Okay? That is decreasing return to scale. Constant return to scale, that kind of thing happen. Okay, input doubled, output also increased proportionately, then constant return to scale. So increasing return, so we know that if we look at long-term data of capitalist development, we can find a sort of increasing return to scale. Same, right? So that is also related to technological change. Decreasing return to scale. Return to scale needs not be uniform across all possible levels of output. For example, at low levels of output, the firm could have increasing returns to scale but constant and eventually decreasing returns at higher levels of output, right? So return to scale, right? Output relation of output change when input change. Input doubled, output more than doubled. That is increasing return to scale, right? But in the next chapter, we also study scale economies, economies of scale, economies of scale. Economies of scale said how many output changes, right? How many output changes when cost changes. That is economies of scale. Cost doubled. For example, output more than doubled. That is economies of scale, right? So increasing return to scale and economies of scale is very similar story, but this is a more wider concept, right? This one includes increasing return to scale. So increasing cost means increasing input or some price of factor also changes, right? This is a more broader concept. So economies of scale. So decreasing return to scale is related to this economies of scale, similar way. Okay? And one famous, that is economist conclusion that in the long run, economies of scale is really important. Because of economies of, we can find economies of scale in the long run, right? In the very long run. Because of that, we can become richer and richer, right? We can produce more and more, and we can consume more and more, okay? So look at the figure of return to scale. For example, labor, originally you here, now you're moving here. Labor input doubled 5 to 10, capital input doubled 2 for 4. So production is now doubled 10 to 20. That is constant return to scale, isn't it? Now think about this. Input doubled, output doubled, then your production is 10 to 35 like this. That is increasing return to scale. Okay? Also, return to scale in carpet industry in the United States. I'd like to skip this. Okay, now chapter 6 finishes.